Ishan Rao. I'm a PhD student from Indian Institute of Technology, Tirupati, and this is my third live interaction session for data analytics with Python. And in this session, we are mostly going to discuss for probability, which is the second part of the course. I know we have been I have been this term little lost behind, but what I have been observed that it with respect to probability, it has the course has given a limited set of understanding. So what I will do maybe in this session and based on the reaction maybe in another session. This session I will talk about mostly discrete random variables and distribution related to that, and maybe in the next session I will be doing the continuous random variable. So we will discuss about what random variables and all that. We will solving some problems in these sessions. With respect to coding aspect, I think if you have seen the week 2 and week 3 videos, I think most of the Python codes are just you have to apply the function for that. So if you're going to do that, you can do that, but you will not get a intuitive understanding like why you're using a certain function from certain library. That's why I'm going to solve certain simple problem, basics and some derivations, which has not been covered in the courses to get you understanding that how when you say binomial distribution, Poisson distribution, normal distribution, how they are actually everything is related to each other and how it makes sense. So two things. It's a 2 hours of course. So we will be taking. I will be doing certain as part of this today's session till 7 o'clock of 6:50 kind of that, following by 10 minutes break, followed by followed by another an hour till 8. Now the sheet that I'm going to show that you're seeing on my screen right now or in your screen right now, this is something, it's the PDF is with me. I'm going to use that to solve or to explain certain concepts or to solve certain things. This PDF along with what I am writing here, along with the whatever the recording that is happening right now, everything is going to be shared by NPTEL, or if you have I'm going to upload this video on my YouTube channel as a requirement, so, and that I will share the link of the sheet as well on whatever I'm writing here. Okay, so that things being clear, let's start with this. So again, if you understand the basic understanding of probability and all that, or random variables, binomial distributions, so it can't be a repeat for you people as well. So if you want to stay, you can stay. Otherwise, for those who didn't understand how, because in courses mostly we have discussed the very definition, strict definition wise. So I thought of let's discuss a little bit more about it, because probability is something which very few people able to grasp it, and you have to practice a lot with this probability to get an intuition behind it. Okay, so that's being said, let's start with the first aspect, which is random variable. So we talk a lot when we're talking about probability, we talk mostly in terms of random variables, or we take the terms event, something like that. But when it comes to distributions, we usually talk in terms of random variable. Random variable, it will tell us about, like if you talk about particular event or something like that, you try to use the terminology of random variable. So let's see what we are talking about. So in a typical traditional variable, so what usually it happens is you might have x plus 10 is equal to something 25. So you have to identify the value of x, or x plus 2y is equal to 3. So you might have to understand, you want to extract the value of x or y. So these are variable with certain values, certain and specific values. These are traditional variables, like it can contain certain values but only a specific one, or if you want to change that value, it can be changed but only one value can be there. But in terms of when we say random variable, this thing doesn't hold true. In fact, the variable itself is a kind of misleading, because let's suppose in a typical probability scenario, we will say that x is equal to, if let's suppose you're tossing a coin. If one, you're giving that if head comes, you're assigning the value 1. If 0 comes, you're assigning, that means it's a tail, right? So you can define usually mathematically, x is a kind of random variable, and it's mostly written in capital letters. So there are certain notation that, which people follow. So but if you observe here, for a random variable settings, uh, x can contain 0 and 1 values both, based on a certain condition. So it's a kind of mapping that is happening. So a kind of mapping is happening between a certain process and a number. Okay, so if you have read already, if you have studied that the aspect of uh, random variable, they usually say that it is usually quantified, right? So when we say quantified, it through this way, that we have some random process may be uh, a tail, like yeah, sorry, a flipping a coin, or whether whether rain is going to happen or not. So these are some random processes. We don't know when it's going to happen, how much it's going to happen, and this is something we can do in multiple times, infinite times, or certain times. So these are some random processes, and for this we're defining them in a certain values. So random variables is just a mechanism or notation that they are giving. We have been got to define them in a much quantified way. Okay, now basically why you're saying that, why we should use them, it's basically to provide a certain kind of notation. So if we are saying that, because as we go deeper, like with we are dealing with more distributions and all that, we have to define a certain way. So for example, why it is useful, let's take an example for that, like how this notation is helping us a little bit, or basically it helped notation a lot for us. So let's say you throw a dice maybe 6 times, and you want to find the probability that sum of all the throws that you have done, sum of them, all throws should be greater than or equal to 30. Okay, so this is a kind of event that you are following, going to tell like that. But instead of telling this events multiple times, you can have multiple situations. uh, so instead of writing all this thing, I can write that y is a multiple case scenario, maybe sum of throws, of dice throws. Here I can just tell that sum of throws which is greater than or equal to 30, or event or random variable which is that which is less than 30, or sum of dice throw which is y it is equal to or less, equal to 15, something like that. So it is giving a shorter notation for us to understand that what event we are going to observe on, and how we are going to access, how we are going to utilize them to solve the problem. Okay, so it's basically for better understanding that we are using a random variable. Now, so in short, if I have to say, it's basically what we are doing is a mapping between random process and its quantifiable value. Now this values we have to extract, whatever quantifiable values we are saying, we might have to extract the probability, right? So what, so we are using random variable, we are defining that random process through a certain context, maybe like for example sum of all throws in a dice which have done 6 times, and the sum should be greater than 30. Same in the same way, you can do much more. So sorry. Okay, now random variables can be of two types, and we are for and all the probability is basically is dependent on that. So when we say random variable now, right now you might consider them as a function. If you're considering as a function also, it does still make a sense, because you're trying to map certain values with the certain aspects or certain events. That's why. So random variables are discrete and continuous. So now here many people get confused, like discrete is easy to understand, like you are saying flipping a coin. So it will get only two values, either head or tail. So no in between, right? Dice, you will get the, and when we're saying die, we usually talk about the upper phase, where whatever the value we got at the upper phase. So we will get 1, 2, 3, 4, 5, 6, something like that. But continuous, it will be like, so if you want to ask a continuous variable, it will be like how much rain or how much quantity of rain happened today, tomorrow, doesn't matter. So for example, here you will say that maybe 2 inches, or you may say that 2.1 inches, or you may say 1.999 inches of rain happened. So it all these are valid values. Even you can say that to 0.0001 inches, this still a random, this still a valid value. So continuous variable is something where you can't list it out. You cannot list out all values. I will show you through one example. And discrete, you can list out all values. Even though you are talking in terms of lakhs and numbers, still you can list out. But if you are saying that a rain is happening and it's between 1.9 to 2 inches of rain, at that point also you have infinite amount of numbers. That is something you can't even quantify, right? So that's why these are such kind of scenarios where you have to use instances where the values, the list of sample space is very much infinite. At that point of time, you use continuous random variables where it's you can quantify or you can count them or you can list them out, all the values like head or tails, or 1, 2, 3, 4, 5, 6 as our dice, or list out the values, all possible values. That means it's a discrete random variable. To give a better sense out of it, um, let's do a small example for this. Let's take a small example for that. So what we will say is, now for, let's say, for discrete we are doing, now we will say that number of heads after 3 flips of coins. Okay, so that means we have to identify that how many number of times, how many number of times the head comes up when we flip 3 number of coins. So x can be, so that means here we are taking x as the number of heads occurring. So this can be counted at head can come 0 number of times in 3 flips, it can come 1 number of times, 2 number of times, 3 number of times. So x random value can have, random variable can have all these 3 values. Okay, so now we have to calculate we have to calculate that how much what is the probability of all these scenarios. That means if I am saying x is equal to 0, so how many, so that means no heads, that means all tails would have come in the 3 instances. So at that time, how we are going to add, what is the probability of that situation? So for that we have to create sample space. So I'm quickly creating a sample space for 3 flip of coins. So it can be, I'm writing in the side, so HHH, HHT, STH, THH, HTT, THT, TTH, and TTT. 1, 2, 3, 4, 1, 2, 3, 4, 8. Okay, so these are the normal typical sample space. So when we find that x equal to 0, that means no heads are given. So we can identify that this is talking about only tails. So we can say that these are 8 8 sample space, so out of this only one time it's occurring. One time is the possibility that all 3 tails are there, that means no heads. Similarly, if x is equal to 1, that is only one time head came during flipping of coin. At that point of time, it may be like scenarios will be like one time head. So this will be the case, this will be the case. I don't think so anything else, and this will be the case. So in this case 3 times it came, so we can say 3 by 8. Similarly, when heads came 2 times, so that means this case, this case, this case, this is a 3 by 8, and p x equal to 3, that means all 3 time head came, that is this, that is 1 by 8. Now this number obviously you can identify, but the interesting part is here is we will see like this. Now if you try to plot graph of this, and let's say here you have 0, it's 1 by 8, and it's 3 by 8 somewhere here, and somewhere here it's 1. Now for x is equal to 0, when the random variable is 0, so you got that 1 by 8 probability. Similarly, when you have x equal to 1, x equal to 0, x equal to 1, you got 3 by 8. Similarly, 3 by 8 when x equal to 2, and again x equal to, when x equal to 3 is there, you got 1 by 8. Now the distribution that you are seeing here, this distribution is something you call, it's basically you call it as uh, distribution function, or distribution function, the probability distribution function that you call it as. Now this is something you might easily understand this, but now here the one thing that the thing that you can change here is, now instead of 3 flip of coins, I take 5 million times. 5 million times I do the flip. At that point of time, if I try to trace a certain thing, and assuming that this value obviously will change, and it will be between 0 and 1. So if you uh, try to plot it, it will be look like this, which you call as bell curve, or a normal distribution in this, like this. Because 5 million points will be too, it's too big, and if you want to portray that in a normal graph, so many points will be there with so many different values, and this region, the highlighted black region, then will become a density function, because the values will seem to be like continuous. And in that scenario, when you have to calculate the what is the probability or something like that, suppose in between x, in this scenario I'm highlighting here, the black one, at that point of time you have to calculate the area under the curve to find the probability. uh, to take it in as a different example. For this, we have talked about, let's assume that we have x again, which tells about find uh, how much rain in quantity, in terms of inches, has happened, in inches has happened. Okay, so this is the thing, and let's suppose that this is some kind of this is a continuous variable, random variable. So we got certain graph like this. Okay, now here if you want to extract the probability that I want x is equal to 2, that is 2 inches of rain. So it may be, suppose here like this, it will be here 2 inches of rain is happening, and here some probability is given, some probability of that event is given, and here the quantity of water which has been rained. Okay, now if you try to find out here, the chances will be that you will get the answer directly as 0, because it's a continuous variable. So what you have to do is, the reason you get 0 is because here under this scenario there will be, you cannot tell that exactly that when you saying 2 inches, that means 2 inches itself is different from 0.001 or 1.99999. So there's lots of number in between, and we are saying that we need exactly 2 inches of rain. It is almost impossible to identify that what is the 2 inches of rain would be, because the possibilities between that there's a possibility that the rain would be even after 2 inches also a certain rain might happen. Even a single molecule will increase the value of inches, right? So we can't do the 2 inches of rain. So what they propose usually is that you take an interval in between. So if you want to identify that what's probability that the rain has happened for 2 inches, at that point of time you put a probability like 1.9 into uh, x into 2.1, something like that. So the probability that 2 inches of rain might have happened will keep the interval of 1.9 inches and 2.1, and whatever rain has happened, you calculate the area under this interval. So once if you try to identify the value of this area using using density functions, is called probability density function if you try to identify the uh, area of under this curve. So if you find these values, then you get the probability of how much rain it might happen, which is almost near to about 2 inches of rain. Okay, so that's a little bit concept of random variables, which have discrete. With discrete you get mostly distribution function, and with continuous random variable you get a probability density function. Today we are going to focus on only on discrete functions, mostly binomial distribution, and if we get time, Poisson distribution, and we'll solve most of the question in binomial distribution. Okay, so if someone has had Ganesh Sai has raised his hand, yeah, please, we can ask the question. Mostly if you better if you type in chat, because if I can't look at the screen both the time at the same time. So if you have any question, Ganesh Sai, please let us know.
No, sir. Thank you. Thank you. No.
Okay, okay,
Wrongly, I pressed it.
okay, okay. So let's start with, so right now till now what we have discussed is a random variable, which basically are not a traditional random variable. It's more like a function which maps a random processes with a specific quantifiable value. It has two different type of variable, discrete and continuous. We mostly focusing today on discrete random variable, that is has fixate values. We are not going to change those values, and which are countable. Um, and we talk about the distribution function and the probability density function in a very brief way. Now, taking that example forward, we will focus on binomial distribution. Okay, so okay, so let's start with an example of binomial distribution and see that how we can uh, understand binomial distribution over the period of time and why it's called binomial distribution. Okay, so let's start with this. Okay, so let's take an example that we have a random variable x, and we are saying that number of heads, hash is number of, I'm writing as a short form, number of heads from flipping a fair coin. Fair coin means it's not it's unbiased, and it gives an equal chance for getting head or tail coin five times. Okay, so we have to find that those scenarios. That means it can be h like this 5 times, or it can be at h t, just like that. There were multiple combinations will be there. So in those scenario, we will try to find out the possible outcome. Sample space will be, since each coin has two outcomes, either head or tails, we will say 2 times, like it can contain two outcomes. So 2 into 5 times, that is 2 raised to 5, that is 32 outcomes can come. If you, I'm assuming that you understand that how it can come to 32, because this 5 time h, if you try to arrange them in a different order with different kind of heads and all that, just like we did for 3 times of coins, you will get 32 different outcomes. So possible outcomes uh, by flipping a coin 5 times will be 32. Now what we have to see is, uh, now we are saying that px is equal to 0. That means probability of getting a head 0 times. Okay, so number of heads we are talking about, the number of head here is 0. So in this case, when you are not getting any head, that means it has only one possible outcome, that is t t t t t 5 times t, that is all flipping coins it has tails. So there's only one outcome that you can get like that, so you can just write it down as 1 by 32. Similarly, px is equal to 1, that is head getting heads one time. So it can be written like h t t t 4 times t, and you replace this h to any of these four position, that you can do another 4 times. That means you can get maximum 5 outcomes where you change the position. Like for example, t h t t t, this is one another outcome that you can get, or t t t t h, this is another outcome. So 5 times 32 you can get like that. Now instead of doing like this for most of the cases, uh, for small example like this it makes sense, but uh, if you increase the timeline, increase that 5 times to maybe 100 times or more like that, it usually doesn't make sense to calculate that in a manual fashion. So what they provide is, they provide the combinatorics. Combinatorics means we will use the concept of combination, permutation, combination here. So what exactly combination? That means what we are doing is, we have a definite outcome. Now we are going to see that without replacing them, we are changing its position. So in this case that you have seen, h has been replaced, can be replaced 5 times within a 5 places. So h can be first here, h can be second time in the second position, similar like that, h in third position, so on. So for the mathematically how you can calculate is, you can calculate using combinatorics. So the formula would be like, since you're flipping the coin 5 times, you will say phi c2, and you want 2 heads. Okay, so you will get phi c2. I'm assuming that you have a basic idea of combination here, so I'm just uh, discussing basic on top of it, phi c2, and then you will try to identify p and q, uh, 2 and phi minus 2. So we'll discuss this also. Okay, so what is pe here is, P is small p, not big P. Small p is like probability of getting a head, that is 1 by 2. Q will be getting a tail, that is also 1 by 2. Okay, so it's like phi c2, 1 by 2 and 1 by 2. Now in this combination of binomial combination, we are saying that the success rate of success rate of 1 by 2, that head in this case will be 2 times, and the failure rate will be 3 times here, that is 5 minus 2 by 3. So if you have to again write it down in a manual way, we can say like this, like, if we, let's take different color. So we have h 4 times, we have two h's here, so this can be one scenario. So in this, if you try to tell that uh, what is the probability of this, you just calculate that 0.5. T also has 0.5, 0.5 into 0.5 into 0.5. Okay, now this and this is P, first and last, and in between is Q. So if you observe this, it will be like P raised to Q and Q raised to 3. 3 times Q is same value, and P has 2 times value. So that's how we are putting it here. So similarly, this will be constant, and we have to change the phi c2 value, that is number of times the position can be changed. Now this h can be positioned in this phi position value in multiple ways. So for that we are calculating it using phi c2 value. So if you calculate it, so for combination, if you try to do, So you will write it 5 factorial into 2 factorial minus 5 minus 2 factorial. In this case 5 factorial, 2 factorial, 3 factorial, and if you try to solve it, it will be like 5 into 4 into 3 factorial. 2 factorial's value is 2 and 3 factorial cancel 2. This will be amounts to 10. And if you calculate this, it will be 1 raised to 32. It will be like 10 raised to 32. Just a minute. Okay. Now similarly, if you calculate for px is equal to 4 or px is equal to 5, that means you're getting 4 head or 5 heads. That means you have to do that 5, that is the number of time your coins are flipping, that is n. Number of time head you want heads, that is 4 here it will come. The probability of getting a head, that is it will be 4, and probability of getting a tail, that is 5 minus 4 equal to 1. Similarly, 5c5, for if you want to have 5 heads, probability of getting a head, that is p raised to 5 and q raised to 5. So this is something of basic understanding of binomial distribution. The reason why it's binomial is two things. First, the reason why it is binomial is binomial. First, it has only two outcomes. Only two outcomes, that is success or failure. Okay, so that is the first reason that it has. That is, when we're seeing p and q, apart from head you can get only tail. So that is only so if getting a head is a success, getting a tail is a failure. So it has only two outcomes. It works only on that. So whatever question you find only two outcomes are there, there's a high chance it's a binomial distribution. Binomial, you have to apply binomial distribution. Second reason that why it is a binomial is because of the combination. Here whatever the outcome is there, it comes with replacement. When what we are saying replacement is, suppose we are getting head in a five position of head that we got. Head can be head h can become either the first, either the second position, third position, fourth position, five position. So it can be replaceable at different positions. So whatever the outcomes that you are coming with, uh, whatever the values you are giving with respect to head, it can be replaced to different position. There we have to apply combinatorics, that is combination formulas. So once you apply those things along with the value that that event can has only success or failure values, at that position time you use binomial distribution. Okay, now let's take another example apart from head and tails. So let's assume that I am playing a basketball. Okay, now the basketball, I'm telling that that probability I'm playing a basketball game. Okay, okay, the probability that I will score is 70%. So and the time I throw a ball to a basket is 70%. So that means the where I don't not score, it will be 100 minus 70, that is 30%. If you write in a decimal way, it will be 0.7% and it will be 0.3%. So if I am in a basketball game, if I am trying to score, 70% chances that I will get a basket, or 0.3% chance that I am not able to get a basket. Okay, so if we have this, so if you want to, the question would be like, find that exactly that I have attempted 6 times. I've tried to throw a basketball in to a basket 6 times. So exactly how many times I can score 2 times in 6 attempts. So I 6 times I throw the ball. So I just to know that exactly 2 times I need to know that exactly 2 times I need to score in those 6 attempts. So what is the probability of that? Okay, so that will be like, if I have to manually understand this, I have 6 attempts, so I can score maybe at the first point. I may not score in the second point. Third time I can score, and rest of the 3 attempts I may not score. Similarly, if I interchange them, so I can say I for first attempt I'm not able to score, second attempt I'm not able to score, third attempt I'm able to score, fourth attempt also I'm able to score, fifth attempt not able to score, sixth attempt not able to score. So it's like that. I have to find all the instances where I'm able to score. So instead of doing all this manually, we can use binomial distribution in this case, because here I have only two uh, outcomes here, that is either I can score or either I cannot score. So in this case here so it will be the exact formula of binomial distribution is NCR P, the probability of getting a success raised to R, and probability of getting a failure minus N minus R. So in this case, I have N will be 6 because I am doing 6 attempts. In that, I want exactly 2 scores. So R will be 2 in this case, and probability of scoring is 0.7, that is it is equal to P, and 0.3 of not scoring is equal to 0.3. So if I apply this values here, so it will be like 6 C2.7 raised to 2 and 0.3 raised to 4, that is 6 minus 2 is equal to 4. So whatever the values I will get based on that, I will apply that. Okay. uh, okay, so anything else? So I'm not solving. I'm usually whatever question I'm going to solve, I will solve this here, or max to max I will apply a little combinatorics where I will say 2 factorial, 4 factorial, and just we have to calculate the value. Okay, so this is a basic examples of binomial distribution. What we'll do is we will go to specific questions and we will try to solve them one by one. So by this time, any one of you has any questions, please let me know. Okay. Okay. Uh, if you're not able to understand certain concept, please let me know through the chat at least, or you can unmute yourself as well. Okay. Now I'm going to take with some basic question and we'll go a little bit to medium size till where NPTEL is usually giving you the questions like that. Now the first question is, find a binomial distribution of getting a 6 in 3 tosses of unbiased dice. So I need to know that how many times I will get a 6 if I am throwing uh, throw a dice in 3 times. So if I have to do that, so I will just say that random variable. So I will have to define random variable. So random variable defined as of probability of getting a 6. Okay, now I can get the 6 in 3 tosses. So I can get the 6 either I may not get a 6 in any of the 3 tosses, or I may get the 6 in 1 toss, 2 toss. I may get 6 one time, I may get 6 2 times, or I may get 6 3 times. So I am defining the random variable like that. Now since I am doing 3 tosses, this will be my n. So n will become 3 because I am doing I'm going to repeat the experiment 3 times. Now if I am going to do that, now I have to define the value of P, that is probability of getting a 6. Now probability of getting a 6 in a dice is usually 1 by 6. So dice will have 1, 2, 3, 4, 5, 6. So probability of getting a 6 is 1 by 6, and Q will be like 1 minus 1 by 6. So probability of not getting a 6, which is equivalent to 5 by 6. Now I have these conditions are set. So usually in a binomial distribution, I will have the formula as n of getting a probability as NCR P raised to R Q raised to n minus R. So this is formula we are going to have in. So for all these 4 scenarios, that is, I'm not getting a 6, I'm not getting a 6 on any of the tosses. I'm getting at least 1 6 from 3 tosses. I'm at least getting, or I'm getting 2 6s in 3 tosses, or I'm getting 3 6s from all the 3 tosses. So for all this, we have to calculate all these values. So that means when we have to do Px equal to 0, identify Px equal to 1. For all these random variable particular values, we have to identify its probability. Okay, so if we directly apply these values, that is n is equal to 3, r will be this value here. We are keeping x equal to r. So whatever the chances of getting head is there, 0, 1, 2, 3, we are going to use that. So it will be come out to be, sorry, 3c0, and p is a 1 by 6, 1 by 6 raised to 0, and 5 by 6 raised to 3. So whatever value we will get, we will see that. Similarly, in this 3c1, 1 by 6 raised to 1, and 5 by 6 raised to 3 minus 1, 3 minus 1. So here we will get 2. So we will have to calculate for that as well. Similarly, we are using directly this formula. We have identify n, we have identify r, we have identify p and q as well. So we are just putting them in those values, in those formulas, and we're getting the probability out of that. So 3c2 1 by 6, 2 5 by 6, 1, and 3c3 1 by 6, 1 by 6 raised to 3, and 5 by 6 raised to 0. Now I'm not calculating here. I'm assuming that you may know that how to calculate 3z0, 3c1, 3c2, 3c3. I'm just what we are going to do mostly in this is we are going to identify these uh, n, r, p, and q values. So I just so if you try to calculate it, the values are mostly will be like 125 by 216, 25 by 72, 5 by 72, and 1 by 216. I have written down this. I have noted down this answer somewhere, so that's why I'm not calculating, because it needs a lot of calculator on that. So we are not spending time on calculation. We're just going to reach to a stage where we just need to calculate a certain value. Okay, so if you want to know the binomial distribution of this, of getting a 6, you just need to find the value of these 4 values, and then if you want, you can plot them also. You can plot them in x 1 2 3. It will the value of x, and here the probability. So maybe we have to change everything in a 216 format, and then we can we can make a distribution, something which supposed to become like this. Okay, now let's go to another question. Let me see, I have question doubt here. No, Abhishek, the 3 times, it will not have 3 times. I will have 4 scenarios of getting a random variable as 0, 1, 2, 3. The 3 will be that all the 3 tosses I'm getting 3 heads. So 3 6, 3 sixes. So those scenario also I need to account for. Now the second question will be like, find the probability distribution of number of doublets uh, in 4th rows of a pair of a dice. So doublets is usually, when we're saying in a pair of dice, it will be like 1 1. So if we are doing dices, that means it has 36 outcomes. In this, doublets will be like 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6. So a pair doublet, we have 6 kind of pair of doublets we can get, and we need to find the probability distribution of number of doublets in 4th rows. So that means we have n is equal to 4, and random variable is getting a doublet from these 4 rows. So what the values will be of x would be like 0, 1, 2, 3, and 4. So what does it means is, if I'm trying to get a doublet here, there's a chance that I may not get a doublet, that is 0 probability for that, I'm not able to get. Or out of this 4th row I may get one doublet, one doublet, pair of doublet, or out of 4th rows I may get 2 pair of doublet, out of 4th rows 3 pair of doublet, and so on. So I have these 5 different scenarios that I need to calculate the probability distribution for. This is one thing. I have n equal to 4, which is already defined. Now probability of getting a doublet is, here out of 36 combination that we can get in a pair of dice, we are pair doublet might come 6 times. So we have 6 by 36, which is equal to 1 by 36. Say 1 by 6. Okay, so probability of not getting a doublet, it will be 1 minus p. So I will just write q here directly. 1 minus p, that is 1 minus 1 by 6, 5 by 6. Okay, now the only thing that I have to do we have to do here is we just have to calculate for p x is equal to 0 when there is a no doublet in the formula of NCR. Okay, let me write it down here. 1 is equal to 2 is equal to 3 is equal to 4. Okay, so I just need to write in the formula of NCR P R Q and minus R. Okay, the R value is here 0, 1, 2, 3 and 4, and P value is 1 by 6 and Q value is 5 by 6 and N is for R is 4. So we just have to write 4C in this case 4C0, 1 by 6 raised to 0 and 5 by 6 raised to 4, and then we have to calculate like that. Similarly 4C1 4C1 1 by 6 raised to 1, 5 by 6 raised to 3. Now I'm doing in a shortcut manner, so let's so I hope you will to catch up in this. 5 by 6 by 2, 4C3 1 by 6 raised to 3. We are putting R value here directly and uh, subtracting this R value with N in 5 by 6, and 4C4 1 by 6 is to 4, 5 by 6 is to 0. Okay, now this is the probability distribution we'll get. If we solve with this value, we'll get some values, and then we can tell it that this is the probability distribution for this question, that of getting a number of doublets in 4 throws for a pair of dice. Okay, by this time everyone is clear, like, or have any doubt, or you're not able to get, or some it's all everything going by bouncer, please let me know in the chat. Okay, 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 so I will solve one more question here before we take a break for 5-10 minutes here. Okay, and based on that we will solve some more question, and then undo that. Okay, so okay, could you please consider why you consider 0 x equal to 0? So x is equal to 0 is for the scenarios where you throw the pair of dice 4 times, but in none of those 4 throws you get a pair of doublet. That is, I am not getting any values, or when I am throwing a pair of dice 4 times, none of these 4 times I am getting any of these values, that is 1, 1, 2, 2, 3, 3, 4, 4. Okay. I hope you can understand, able to understand that. If not, please let me know one more time. Kshitij, please start with the basic in the question. Or Kshitij, so what basics you are asking for? Is it you are asking for basics of probability or basics of binomial distribution? Please let me know in the chat, because these are actually a basic questions. Okay, can you please explain again how we get P of doublet 6 by 6? Okay, for that, okay, let me do one thing. Okay, so for that you should know that how a pair of dice will get. So if you throw a pair of dice So what kind of outcome you may get? So you may get, I'll just use different color. You may, while throwing the both the dices, you may get 1 1, you may get 1 or 2, 1 or 3, just like that, 1 or 6. So in each of this, so when we're saying 1 1, that means in one dice you got 1, in another dice you got 1. 1 6, in dice number 1 you got 1, in dice number 2 you got 6. Okay. Similarly, if you extract all these possible outcomes, so it will be like 6 1, 6 2, 6 3, 6 6. Okay. So if considering that for dice number 1 you got 1, and for the rest of the for the other dice you got the value from 1 to 6, it has 6 outcomes you got. Similarly, if you go from row to column, that means now you change the value of second die 6 times. Similarly, if you change the value of value of first die 6 times, you will get the outcome here also 6. You can change the value of first die also 6 times. That means 6 into 6, you got 36. This is sample space. That means if you throw a pair of dice, there are 36 possibilities that you can get. Okay. Now if you can get 36 different possibilities, that you may get 4 by 5 is also one possibility. So all these possibilities are there. Now doublet is the values of 1 1, 2 2, 3 3, 4 4, and 5 5, and 6 6. In this case, what the number so this scenarios we are getting doublet is 6. I have 6 outcomes which I can call as a doublet, okay, and I have a total sample space of 36. So to get a probability, what is the probability that I will get a doublet will be like 6 by 36. Okay. Now, so another question is, we have considered only 4 conditions, that is 4 throws. So why to consider 5 values? So the Okay, so the 5 values are 4 throws are the throws. Throws are like you're just throwing the dice. The condition, the outcomes they will be different scenarios. The scenarios will be here is like I'll throw the uh, dice 4 times, pair of dice 4 times, but I will not get any pair of doublet. That is 0 value. Or I make from 0 and then 4, that means in all the 4 throws I may get each time I'm throwing a pair of dice I'm getting a doublet. So that's why considering all the scenarios I'm getting that from 0 uh, from no doublet to all the doublets in all the throws. That's why we have 5 scenarios. What is the answer if event is not doublet? Then you have to be more specific of what is not doublet. Like when you're saying that if the event is not doublet, then you have to specify that what exactly you want from the pair of doublet. I can directly answer you like 1 by 6 minus. If the event is not doublet, that means you will have to minus by 1. That is, the probability is 1. That will be the event where you're not getting a doublet is 5 by 6. That is, if you expand it, that means 25 outcomes are there out of 36 sample space which are not doublet. So I'm getting that if this not a doublet. You're getting Surya in this aspect? Okay. It's already 6:55, so we may take 5 to 7. Like let's meet at 6:75. We will solve a little bit more questions on binomial distribution, and follow which we will. I think the time will persist me to uh, derive you the how we get the value of expected value for a uh, for a binomial distribution. Okay. So from 7:5 we will start again. If someone has any question, they can unmute themselves and they can ask, or they can type in the chat. Yeah, Abhishek. Yeah, Abhishek.
Sir, we are using here binomial distribution because it is a place. We have to find the place of this,
Sorry, come again. Like,
that
can you repeat the question?
we if we toss the coin, then we have head tail, and if we toss the coin 5 times, then we have head tails. So we have to find by binomial distribution. Why we find that?
Okay. They might be other ways also to solve the same problem. The reason why we are using binomial distribution is not because you're flipping a coin 5 times or 10 times or like that. It has only two outcomes. Either you will get a head or you will get a tail. Okay, and usually when you're asking for probability, you will take it as, especially in binomial terminals, you will take it as either as a success or a failure. So if you define an event that I need to get a head while flipping a coin, I will take it as a success criteria, and if I get a tail, I will take it as a failure criteria. Now I can represent that using binomial. The reason being, if I'm flipping the coil 6 times or 10 times like that, I will get various combination that in which order I will get a x number of amount of head in a particular sequence. So if I'm taking a flipping a coin 10 times, the order in which 3 head will come in those 10 sequences might differ a lot. So calculate those kind of scenarios, that how many times I can replace the head and in what sequence I may get the head, because sequence also matter here. The number of time I can get the head at any position, I have to calculate that. For that I need to use combination, uh, the principle of combinatorics. So the permutation combination there. That's why we are using binomial distribution. First is it has specific outcome, that is success or failure. Also, that outcome that is coming right now, it can be replaceable. So I can get the same output in a different way, like in different positions. So for calculate that in which how many different position I can get that value, for that I need to use principle of combination. That's why using binomial.
Yes, sir, clear.
Okay. Any other question? It should be used for only for discrete value. Binomial instruments meant binomial Poisson is basically used for discrete values only, not for continuous. For continuous, you will get uniform distribution, normal distribution, other kind of things, other kind of techniques are there for that. Any other questions? Okay, 5 more minutes. We'll wait and then we will start solving the next questions. Can we apply these concepts in real life? You actually do that, and you might heard that, but you usually maybe not able to grasp that how it has been done. So for example, let's take an example for that. You know that elections are coming in Lok Sabha next year, right? So so, so you have a population of 1.4 billion. Okay, but there's something called as opinion polls, right? So they haven't so the opinion polls tell that which political party is more favorable. So how they do that? They are not going to conduct election or going to ask all the 1.4 billion people in India, right? So they will take what they will take. They will take a sample. They will take some small sample base, and maybe hundred, thousands, or lakhs of people, mostly in thousands. They will ask them, and then they will give them options that, okay, party A, party B, party C, you have these options. Who will going to support? So based on that, they will calculate, and they will say that 70% chances are there that party A will win, or 20% chances are there that party B will win. So this kind of scenario, probability use a lot, probability and statistics. And and the thing is, lot of places where now data is everything, so everyone wants to gather as many data as possible and make sense of them. So while making sense of them, you need to understand that the properties of that data, and based on that you have to identify how you can solve it. So probability is just a tool, statistics will is just another tool that you can use them for that. So this is one scenario, the opinion polls, where from 20, 30,000 of people, they will try to say that, okay, 70% chances are that the party A will win. Okay, similarly, you will heard of that of airlines. If you flying a airline aircraft or something like that, they will say that the chances of getting a plane crash is maybe in 1 in 10 lakhs or 1 million, something like that. So how they come up with this number? So what they do is they will go with the old data, and based on that they will try to calculate the what is the probability that another aircraft crash might happen, because we can just only predict it. So wherever the prediction is there, we are giving them a kind of chance. So we are just giving that, okay, this much amount of chances are there that the plane will crash, or this much amount of chances the plane will not crash. So techniques are being applied. It's just that after applying, you have to see more and more in real life how they, you have to ask like how they have calculated. If someone gives you data, you have to ask that how they have come to certain results, and there's a high chance that they will be using the techniques that you might be learning throughout this course or any other courses. Easiest way for t value. What is t value? Can you explain what is t value here? Easiest way for t value finding method, sir. So if you can explain what is t value, then I am able to answer. Okay, so it's almost 7:05. I think I will start. And okay, Abhishek, you have any question? Okay, okay. Let me
No,
start. Okay, so let me start. P-valent hypothesis. I have not idea that what is the shortcut method they are having. We will discuss. Maybe we can discuss at the end of the class. Okay. Uh, okay. So let's start with the question. The question is, find the probability of getting 5 times head on tossing an unbiased coin for 6 times. So I have a coin. I have to toss it 6 times, and I need to get the probability that at least 5 times, that is x should be at least greater than equal to 5. 5 times tossing of unbiased coin for binomial distribution. Okay, so if we have to do that, so first thing, in a binomial distribution, we have defined p and q, that is probability of getting a head in a single toss, something like that. so it will be mostly 1 by 2. Similarly, not getting ahead, I'm just getting ahead in a single toss is 1 by 2. So just write q here. Okay, now instead of if we have p greater than equal to 5, that at least 5 times the head would have come. So we have to assume that uh, so we have to calculate this kind of situation where x is basically getting ahead. Okay, so if we have to do that successfully getting ahead, how we can define this is when find the probability of a scenario where you get five heads in 6 tosses, and find the probability of a head where five you get that uh, more than five headed in at least 6 tosses. That means you're getting 6 heads. So when we're saying at least 5 times, that means you get either 5 or 6 heads in the 6 times you tossing a head coin. So you have to find the values of these. uh, why only still 6? Because we are only tossing a coin 6 times. So to use the formula that is here, I'm just writing it down for just for you to remember. NCR P raised to R Q raised to n minus R. So if we do that, we just have to do 6 C5. 6 is the our n, that is 6 times that we are having, and uh, P is 1 by 2. So 1 by 2 raised to 5 and 1 by 2 raised to 1. In this case 6c5, 6c6 for x equal to 6, 1 raised to 6, 1 by 2 raised to 6 and 1 by raised to 0. It is P, it is Q. So if we try to solve this, you will get some value of 7 by 24. Okay, so so again, so what has been done is like unbiased coin has been tossed 6 times, and we have to find the probability that the heads will come at least 5 times. That means it can get at least 5 times, or it may get more than 5. So in this case, only 6 might happen. So we are calculating the probability when the random value variable is 5 and 6. So once we have to find, we put that in binomial distribution formula, we get a certain value. Okay. Now let's take another question. Uh, in this, there are 4 fuse bulbs in a lot of 10 good bulbs. If 3 bulbs are drawn at random with replacement, find the probability of distribution of the number of fuse ball drawn. So assuming this, so we have 14 bulbs in total, out of which 10 are good bulbs and 4 are fuse bulbs. Okay, now 3 bulbs has been drawn. So if we, so first, since we need to find the number of probability distribution of fuse bulb drawn, so so our P would be like, so P would be like uh, in this case uh, getting a fuse bulb. So it will be like 4 by 14. So we have 14 total bulbs, out of which 4 bulbs are fused. So we get a this is 2 by 7. And Q will be like, which is not a fuse bulb, that is which are good bulbs. So getting a non-fuse bulb, it will be like 10 by 14, that is 5 by 7. So we have P and Q ready. Now they are asking is 3 bulbs are drawn at random with replacement, that this can be replacement as well. Find a probability distribution. So we have to find that when 3 bulbs are drawn, we have to identify that how many number of times a fuse bulb has been drawn. So like earlier, that how we have seen earlier, that when we are taking 3 bulbs out, there's a chance that none of the bulbs are fused. So the random variable outcome will be 0. If 3 bulbs are drawn, at least 1 bulb is fused. That one scenario we have to take. 3 bulbs are drawn, 2 bulbs are fused. That case, and when 3 bulbs are drawn and all the 3 bulbs are fused, this case. So we have to find for the random value variable value of 0, 1, 2, 3. Now let's put that in a binomial, in a binomial. distribution scenario, that is Px equal to 0, Px equal to 1, Px equal to 2, Px equal to 3. So we are going to find a probability distribution in all these scenarios. So it will be like we are taking 3 bulbs, out of which 0 bulb is fused, and the probability of getting a success of fused bulb is 2 by 7, and not getting a bulb is 5 by 7, 3. Similarly, 3C1, that is out of 3 fused bulbs I am getting at least 1. Probability of getting a success is 2 raised to 7, 2 by 7 raised to 1, and 5 by 7 raised to 2, that is 3 minus 1. Similarly, 3 raised to 2, 3C2, that is out of 3 I am getting 2 fused bulbs, and 2 by 7 raised to 2, and 5 by 7 raised to 1. Similarly, if we expand this for x equal to 3, that is all the 3 bulbs I am taking out are all are 3 are fused, 5 by 7 raised to 0. Okay. Now, okay. Now, if we calculate this value, we'll get certain values. So, if we want to calculate that, you can do that as exercise. Otherwise, it mostly will be in the terms of 343 kind of thing, with the denominator base of 343. Okay. uh, okay, so that is this thing. So this is a question for this is a question for fuse bulbs. So usually we look out for good bulbs are there or not. Here we take about the reverse thing in terms of fuse bulbs. Okay, now another question, I think we have one or two more question left in this. Okay, now the question is, on average every 1 out of 10 phones is found to be busy. Now 6 telephone numbers are selected at random. Find a probability that the 4 of them will be busy. Okay, so this will be like, so the event will be like P getting a phone busy, busy is 1 by 10, that is every 1 out of 10 telephones is busy. So I'm getting a busy phone is be 1 by 10, that is not getting a phone busy is equal to 1 minus 1 by 10 is equal to 9 by 10. Okay, now the question is 6 telephone numbers are selected at random, that is n equal to 6, and they are saying that find the probability that 4 of them will be busy. So for x is equal to 4, that is 4 telephones are busy, numbers are busy, I have to find a probability for that. So x is equal to 4. So I have to put that these values all together. Here r is 4 in this case. So 6 out of 6 telephone number that I have extracted, 4 I am expecting to be busy. In that the success rate will be 1 by 10 raised to 4, and the failure rate will be 9 by 10 raised to 6 minus 4, which is equal to 2. If you try to solve this number, you will get some value of 0.001215, something like that. Okay, uh, so this is also like, once you get able to make your equation, you able to find all the parameters of this NCR P raised to R Q. So you have to find the values of N, R, P and Q. If you are able to identify these 4 values, most of your all your answer will be solved. So mostly if you get P, you can extract Q, that is because it will be mostly like Q is equal to 1 minus P. N you will get mostly from the quotient, and R also you mostly get from the quotient. So here 6 telephone numbers we have taken as sample space random. From that sample we are finding whether 4 of them will be busy or not. So for that R equal to 4 and N equal to 6. Any doubt with this question, please type on the chat. And meaning of at least and at most in mathematics. Okay, Abhishek, we can discuss about this later, about at least and at most. Okay. Now another question is, okay, I think we have 3 more question left. You will find the recorded live session. I will share the YouTube channel link, or otherwise NPTEL will share this recorded live lecture and with this PDF also. Uh, okay, so the next question is, if a bias coin is tossed. Okay, so it's not unbiased. That means we cannot say that head or tail is probability of getting a head is 1/2. It's not, because of bias coin. So we cannot say that this statement holds true. So what it say? Let's say the probability of getting a head is 3 times more than probability of getting a tail. Find the probability distribution of getting a tail if the coin is tossed twice. Okay, so what it's saying is, first we have to find the probability. So since it's talking mostly about tail, so let's say that P getting a tail is P, and getting a head is 3 more times than probability of getting a tail. So that means, let's see, let's say some value of a, okay, and getting a head is 3 more times than getting a tail, that is, it will be 3a, okay. And then usually if you add the value of getting a head and getting a tail, the probability will be 1. So head plus probability of getting a tail is equal to 1. So that is a plus 3a is equal to 1, 4a is equal to 1, a is equal to 1 by 4. So probability of getting a tail is 1 by 4, and probability of getting a head is 3 by 4. Okay, I hope you will understand that how I'm got this. According to the question, getting a tail is, if I'm assuming a value a, and getting a head is 3 more times than getting a tail, that is 3a, then I will add this value a plus 3a, which should amount for equal to 1, that is whole probability 1. From that I will extract the value of a, which turns out to be 1 by 4. Okay, now the main question is, if I get a tail, that is if I'm getting a tail, how many times I will get a tail if I toss the coin twice, coin it twice. So I will, if I'm tossing the coin twice, either I will get 0 time tail, either I will get 1 time tail, or I will get both the time I will get the tail. So I have to find, scenario for x equal to 0, p x equal to 1, and p x equal to 2. Here my n will be 2, r will be this 0 1 2. So let's, if I do this, so it will be like 2 c 0, r, my getting a success of getting a tail is 1 by 4 that I identified earlier. So it will be 1 raised to 4 by 0 because of r, and 3 raised to 4 of getting a head, it will be 2. Similarly 2c1 getting a tail 1 raised to 4 by 1, and 3 raised to 4 by 2 minus 1, which is equal to 1. Similarly 2c2 1 raised to 4 by 1, 3 raised to 4, say 2 raised to 2, 1 raised to 4, 1 by 4 by 1 by 4 raised to 2, and 3 by 4 raised to 0. So if I calculate this, I will get some value. These are the probability distribution of getting a tail if I toss the coin 2 times. Okay, the question is, what is biased and unbiased coin? Okay, so the biased coin, unbiased coin is, see, if I am having an unbiased coin, that means the probability of getting a head and probability of getting a tail, they are same. That is 1 by 2 and 1 by 2. Okay, that is the biased coin. I am unbiased coin having that both the chances of getting a head and tail is equal. But in biased coin, I cannot assure that the probability of getting a head and probability of getting a tail will be equal. If I have tweaked the coin little bit, this because of certain things, or if I did something with the coin, there's a high chance that I may get the head more number of times rather than tail. So that will become a bias coin. Okay.
Excuse me, sir. Excuse me.
Yeah.
Can you please move that left top bottom that image down, sir?
Okay.
Right bottom, right bottom. Are you
Mm,
calculated? Okay.
yeah. Okay, so bias coin can have both side head, both side tail, or it has been tweaked in such a way that I may get a certain value more number of times come with respect to the tail. So that what will become bias coin. So if you have heard this in Mahabharata, Shakuni has certain kind of dice. It has been tweaked. So it has been tweaked that whatever the number the Shakuni wants, based on that, the number will be you will get that number in the dice. So that is a biased dice. Similarly, unbiased and unbiased coins, it will be like that. Okay, so okay, so let's do this. Okay. Okay, so the next question is, I have a bag. I have a bag with 5 green balls and 3 red balls. And if 2 balls are taken as a randomly from the bag with replacement, that means once I take a ball, I will take out. I will see what is the color of that ball is, and I will again put down. So again, I will take another ball. So the number of balls in the bag will remain the same. So if I do with replacement, find the probability distribution of number of green balls drawn. Okay, so here I have to find that P of getting a green ball, probability of getting a green ball, I have to find that. So I have 5 green balls and I have total 8 balls, that is 5 plus 3. So it will be like 5 by 8. So I have total 8 balls, out of which 5 balls are green. So probability of getting green ball is 5 by 8. Similarly, probability of getting not a green ball is 3 by 8. So the red balls, I'm not taking red name because it's better for us to talk in terms of green, because everything is question around revolves around green balls. Now I have P and Q with me already in place. Now what I have to need down, the main question is that 2 balls has been taken drawn from the bag randomly. Now I have to find the probability that the number of green balls drawn. So whenever I'm taking 2 balls, so what is the probability that I will get all these balls together? So same concept. So when I'm drawing out 2 balls, so scenarios will be like, when I'm taking 2 balls drawn out, that there is zero chance that the 2 balls are green. So might be 2 balls might be red. If I'm taking 2 balls out, there's a chance that 1 ball might be green. If I'm taking 2 balls around, then both balls are green. So these are scenarios, and so the probability that I need to calculate will be like x equal to 1, x equal to 2, and x equal to 0, 1, and 2. Okay. Now R value will be 0, 1, and 2. That is based on the number of green balls that I might get with each draw. So for probability of getting that is 2C0, that is out of 2 balls that I have drawn, 0 balls are green, and getting a ball is 5 by 8 usually. So 5 by 8 raised to 0 and 3 by 8 raised to 2. Similarly, if I get a 1 ball, green ball, so success rate is 5 by 8 raised to 1 and 3 by 8 raised to 2 minus 1, which is equal to 1. Similarly, 2C2, that is 2 balls are taken out and all 2 balls are green. For that, 5 raised to 8 by 2, 5 by 8 raised to by 2, and 3 by 8 raised to 0. That is 2 minus 2 equal to 0. So once I calculate this value, I will get the probability distribution for the particular question that I am having. Okay, so I think this is almost over with the kind of question that we are having here, I guess so. Uh, let's see, I have another question. Okay, so I think this is the last question. Okay, last question of this is, find the probability distribution of getting a number of 4s in 3 throw of a dice. Also find the mean and variance of the distribution. So for mean for a binomial distribution is binomial distribution is n dot p. We will talk about what is np. We will derive it right now after this question. And variance is n dot p dot q. So n will be in this case the the rows, 3 rows that we are having. P will be the probability of success of getting a number 4 in the dice, and q will be the probability of not getting a 4 while throwing the dice. Okay, so first find out the probability distribution here. So for this I should need to find that what is the probability of getting a 4. So getting a 4 uh, in a throw of a dice is 1 by 6. So I have 6 numbers in the dice, so out of which 4 will get only one time, so that's why it's 1 by 6. So the q will be not getting a 4. 4 will be 1 minus p, that is 1 minus 1 by 6, 5 by 6. Okay, so I have p and q. Now the question is that the number of so I will have 3 throws of a dice. So I need to find the number of time I will get the 4. So the scenarios where will be, if I'm throwing the dice 3 times, will be like x is equal to 0. That is, all in all 3 throws I didn't get 4. At least I would get 1 time. At least I will get 2 times, or I will get 2 times 4 while throwing the dice, or I will get all the time. In all the 3 throws I got the 4. So I need to find the probability of that. So this is n is equal to 3, and r will be my 0, 1, 2, 3. So if I have to calculate the probability, I need to probability distribution. I need to calculate for all all these scenarios. So it will be like 3c0. So out of 3 throws, 0 number of times that I got the 4, and it will be the success is 1 by 6. So 1 by 6 raised to 0 and 5 by 6 raised to 3. Similarly, if I get 4 at least one time in 3 throws, so success will be 1 raised to 6 by 1 and 5 by 6 raised to 2. Similarly, C3 1 by 6 raised to 2 and 5 by 6 raised to 1. 3 minus 2 equal to 1. So 3C3 is 1 by 6 success rate raised to 1 by 6 raised to 3 and 5 by 6 raised to 0. That means all the 3 times I got 4. All the 3 times I got 4s on the dice. So if we calculate this value, we will get the probability distribution for this question. For mean, we just have to calculate n into p. Here our n is 3, and probability of getting a 4 successfully is 1 by 6. So we will calculate that, it will be 0.5. Okay, so mean of getting a 4 for this question is 0.5, and variance will be npq, that is 3 into 1 by 1 by 6 into 5 by 6. So if I calculate this, it will be, just a minute, just a minute, I think, yeah. So I will get 5 by 12. Okay, so variance will be like this, but what I'm going to do now is to make an intuition of why for a binomial distribution, because we haven't defined the binomial distribution mean, and it is required a lot of why we need mean, variance and standard deviation, how we get to this n dot p. So we'll do mathematical definition for that. So okay, 1 by 6, I missed the statement. Okay, Okay, so what I was saying that for this question, the probability of getting a 4 in a dice is 1 by 6. So that's why the probability of getting a success in this is 1 by 6 and not getting a 4 is 5 by 6. I hope you able to understand that, Aditya. Okay.
Sir, how 6, sir? Denominator
6 is like a dice will have 6 values 1, 2, 3, 4, 5. That's why.
6. Oh, that's okay.
Yeah. A dice has 6 faces. That's why. Okay. Now comes to a little challenging part here. Basically, to find basically to find the expected value of a binomial distribution. So expected value of binomial distribution is actually called mean of binomial distribution. So what do you mean a mean of binomial distribution is? Suppose you got a distribution like this, something like this, and this. I got this distribution. By this time, what we are calculating is how to make this graph by calculating different values and make this kind of distribution. Now, if I see this distribution also, I cannot make a sense out of it if I have a very high set of data. So at that point of time, I need a mean, a number which can a number which can tell me that what this distribution is about. Uh, like suppose I'm getting a mean of 0.5, that means out of this binomial distribution between 0 and 1, majority of values lies around 0.5. So that's what it tells about me. So if I have a certain problem and it usually the probability is between 0 and 1, and if I have to identify that what is the mean probability that I'm getting, so for that kind of scenarios, from the whole distribution, I will try to extract expected value of a binomial distribution, which has been directly told as n cross n dot p. So why n dot p is basically because of derivation that we got. So I will do the derivation of that by giving it intuition that how it actually work and uh, and how I can directly extract the meaning of mean from normal mean that we take from a population. I will start that now. Okay. Yeah, I will share the notes. So after this class, I will upload the lecture. In that, I'll upload this video. In that video, I will give the link of this whatever I have written. Okay. Now let's start with normal mean. So how will mean is, suppose we have a population of 3. Let's take different value color. Okay, so suppose I have this number. I have this population. Okay, I have a population of certain numbers. So how will I call that? Find the mean of this population. So what is the average number which I can find at which represent this population is? What I will do, I will add all these things and divide by number of samples I have. So I have 5 numbers, so I divided by 5. So I will get certain value of 18 by 5 and which is 3.6. This is a normal how we calculate the mean. Okay, now let's tweak a little bit. I will try to tweak this equation in a different format. So what I will do is I will write the same thing in a different way. That is 3. I have 3 times plus 4 one time and 5 one time and dividing by 5. Okay, this is one way of looking. Again, I have to more explicitly change it. I'm writing the same thing in a different way, so, because I want to relate this with the probability. So I will write 3 by 5 by 3, 4 by 5 by, or 1 by 5 by 4. That's better, 1 by 5 by 5. Okay, so if I do this, I will get the same thing again. So I'm just separating the terms little by little. I'm giving them a fraction value like that. So if I find the value of 3 by 5, 1 by 5 and 1 by 5, I will get that 0.6 of this into 3 plus 0.2 into 4 and 0.2 into 5. So I I started with this normal typical mean where I'm just adding the number dividing by 5. Now I reached to a point where I can define that as a in terms of decimal numbers. Either I will and either I can interpret this number like this, or I will say like 60% of the number of population that I have has 3, 20% of population that I have has a number 4, and 20% of population that I have is number 5. And if you want to calculate the value of this, you will find the same mean that we got by 3.6. So for example, if I extract this extract the 0.6 into 3 plus 2 0.2 into 4 plus 0.2 into 5, I will find that 1.8 plus 0.8 plus 1.0. I will get 3.6 value. So the value wise I am not changing anything, I am just converted the same mean value into this format from which I can read that for a given population that I am having here, in this I am having 60% of the population has 3, 20% of the population has number 4, and 20% of population has 5. This is something how we usually see in probability as well. Okay, so this is what we have seen, like this is how I can convert that in terms of probability as well. Okay, now what I will say, what the interesting part of here is, now we have done for a number, that number also for a population which is finite. This is a finite population. In this I will get some random sample here. I can find the mean which can represent this whole finite population, like that. Okay, I can do like this, but let's take another let's try to derive it in terms of like how we can uh, identify and get to the number of mean of n dot p. So expected value ex is equal to n dot p. So for a finite population with a random samples, or with considering all the samples, I can find the mean. Okay, with how? Because if suppose I have a finite population like in lakhs, or we consider that this is not a finite population, infinite population, I may not able to access each and every numbers. But what I can access is I might have a frequency of those numbers in terms of percentage, like how I have here 60% of numbers are 3, like that I might get that, and based on that I can find the mean. Okay, Vaibhav has raised a hand. Yeah, tell me, Vaibhav. You can unmute yourself and you can tell.
Uh, Sorry, sir, nothing. I will ask you after the session on this.
Okay, okay. So let's continue with this derivation. So what we are trying to, I'm trying to connect here is with a normal mean. Also, I can give a sense of that I'm calculating a probability of a certain population, a certain values, right? So let's take an example and try to derive based on that. So what I can say is, let's assume uh, let's assume that I have okay, so I have I can so number of basket that I have made, number of basket I am able to make after 10 shots. I need to find the probability of like that, or I need to find the mean of like that. Like the number of time I may throw 10 shots might be infinite times. So based on this I may not able to identify certain values. So what I will do, I just from previous data I know that 40% of time whenever I throw a shot, it will get in. Okay, so if I just extract the value of like this, so what I will say, I know that probability of getting n is my 40%, like out of 4 40%, and if I'm making 10 shots, if I just find an explicit value n dot p, I will get that 0.4 into 10, that is 4. So on an average 10 shots that I am putting inside the basket, on an average I may able to put 4 inside the basket, and rest of the basket I'm not able to get it, right? So this is one way of looking at it. But what if like Uh, okay, so what if like in this, rather than saying 10 and 4, I will say like for n shots, n shot that I had thrown in the basket, only k shot went in. Okay, so if k shot went in, so how I can find the mean value for that? So for that, how we can say is we can look out for probability. We find the probability of that using binomial distribution, which in this case will be like n c k, and p. I'm assuming that p is the probability that my shots will get n, p raised to k and q raised to n minus k. The qs will be the shots I'm not able to take. Okay, now I want to extract upon that. So how I can do that? So nck, I can write it like n or k as well. This is a different format that I can use. Mostly I'm going to use like that. Okay, so this is the scenario that I have. Now to get a mean of that, I need to extract all those scenarios where I put the 10 shots. So I will say that when k equal to 0, n, and then I will put nk, pk, q, n minus k. Okay, so what is happening here is what I did. So find expected the mean value of that. What I did is I try to find all the probabilities of all the scenarios where this k value can be anything and n value can be anything. In those cases, whatever probability I'm getting, I'm adding them up and I'm trying to find the mean out of it. So for that, I did the summation here. So similarly, like if you do like I have 3, 3, 3, 4, 5, what I will do, and it I contribute as a x, so I will just, for finding the mean, I will do that x summation of all these values and divide by the number of samples. Same thing for expected value also. I can represent this probability that nck, p raised to k and q n minus k into this value, into this format. Now what I have to do is, uh, if I try to expand it a little bit more of this equation that I'm getting, equation 1, let's assume that it's equation 1. So I will get that if when k is equal to 0, uh, when k is equal to 0, okay, I will need to put k, 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 k equal to 0. If I'm putting k equal to 0 and whatever the value I will have, n 0, p raised to 0, q raised to n plus, I'm expanding all this value, so n raised to 1, p raised to 1, raised to n minus 1. Similarly, n raised to cn, p raised to n, q raised to n minus n. That is 0 here. Okay, I'm extracting this value and I did like this. So this terminology is equal to 0 because I'm multiplying something with 0. Okay, if I remove this thing, so again I have to focus on this highlighted part of the equation. So let me extract this out. If I write the same thing in this format, so it will be like k equal to 1 to n, k into uh, nk, and p raised to uh, p raised to k and q raised to n minus k. Okay, now if I expand this again, this summation, this value, I will try to expand this combinatorics, that is nck. So I will put like k dot n factorial, k factorial, n minus k factorial, and pk q n minus k. Okay, yeah, Pooja, if I'm doing the derivation, if anyone not able to understand any part of the step of the problem, please let me know that. Okay, so Pooja, you have raised the hand.
Sorry, sir, by mistake.
Okay. Okay, so what I'm trying to derive here is, for those who have joined here, that I'm trying to derive that how from basic mean that we have found usually in normal sample space, how we can derive the same thing for our binomial distribution, the mean of binomial distribution. Okay. Uh, Okay, let's get back to this again, derivation. So I have this expanded form where I started with, let to give an example, to find expected value. What I will did, I put um, I put the probability of finding a particular instance. Just a minute, I will show it one more time. Yeah. So I started with this problem that I can make 10 shots in the basket, out of which k shots will went in. So I need to find the mean of that thing. So for that, for finding any k shots at a particular instance, I may use typical binomial distribution formula. But to find the mean for that, what I will do is I will take a summation of all the scenarios, of all the case scenarios that I am having, and I will submit just like how we do for normal mean. We sum all the particular values in the population divided by certain things. Same thing I have done here, and then now I am doing the mostly the extra. I am expanding it, closing it. So we reach to a point where we are starting from k equal to 1, summation of k equal to 1 to n, k into n factorial, n by k n c k, and the remaining probability value p raised to k and q n minus k. Now if I have to remove k here, I just need to do that. I just remove k from here and put k minus 1 factorial. So k into n, so I will just put n to k minus 1 factorial, n minus k factorial, p raised to k, q raised to n minus k. Okay, now once I got this become little complicated. So let's try to more simplify it. So we know that our expected values are n into p. So I can extract n and p from here, and I will write it like n and p, and e is to k equal to 1. It will look at n minus 1 factorial, k minus 1 factorial, n minus k factorial, and p has taken here. So p, okay, what just happened? Yeah, p, okay, okay, just mixed down. Okay. Sorry, I think it got deleted. Let me write it again. Okay, so what I was doing till here is I'm going to extract NP, which is we know that the value I'm having, and I will put inside every whatever the remaining inside from the equation will be like. I will keep it inside. That is summation of k equal to 1 by k equal to 1 to n. And since I keep n out, so I will keep n minus 1 factorial inside this. Then remaining denominator will be same as it is. And since I have taken p also outside, so I will keep p raised to k minus 1 and q raised to n minus k. So this how I have taken it. Now I have to solve it, this red box, in a such a way that I should make this value 1, so that I will get n is to p. So to do that, let's go down. I will write it down again what I have written above. Mhm. So we have done that np k equal to 1 to n p raised k minus 1 factorial and n minus k factorial, sorry, n minus 1 and k minus 1 factorial and p raised to k minus 1 q raised to n minus k. Now I'm going to substitute certain values. So the values would be like a equal to k, let's take k minus 1, b is equal to n minus 1. I'm just substituting this n minus 1 k minus 1 value in a different way, and n minus k would be like okay, this would be like uh, b plus 1, and k would be minus a plus 1, so it will be b minus a. So if I substitute this above, NP, it will be like A equal to 1 to B, and n minus 1 is B, so B factorial, n minus k is B minus A factorial, and k minus 1 is A factorial. P raised to k minus 1, k minus 1 is A, P raised to A, and Q raised to B minus A. Okay, now if you observe only this factorial, you can assume that this is a binomial factorial that you got. Okay, and it's a summation that we are getting from A to B is usually accounts for 1, because the probability that we are finding, this is a probability uh, of any binomial distribution that having, and summation of all the binomial distribution would come down to 1. So the again this is a binomial distribution, and so I'm getting a probability for each instances from A equal to 1 uh, to B, and for this scenario, if I'm uh, sum of all if this summation will give that sum of all probabilities are usually equal to 1. So if I do that, it will come down to NP into 1. So the expected value of binomial distribution that we are having is NP that we are having. Okay, so I don't know how many will follow this, but this is how what we started from deriving is from a simple statement of a mean, that we how we find a typical mean, that is if we have 3 3 3 and 4 5, from that we can convert this mean statement to a population of to in a format of a probability, where we can tell that how many percent of chances are there the particular number exists, that is 60%, 20%, 20%. Taking that same q like that, we try to solve that how Ex equal to NP can come into picture. So we have taken an example of like if I have taken 10 shots, out of it, if my probability of success is 40%, I can tell that using N and P that is my expected value or mean, that in any time I take 10 shots, there is a chance that at least 4 shots will get in the basket. So we expanded that problem into n shots and into n or k problem. That means in total I will take n shots, out of which k some shots will went into the basket. So how I can solve that? So we can solve that using binomial distribution, that is using NCK value. So using this binomial distribution, I can take it out, but to find expected value, I need expected mean value uh, of that particular instance. I will sum take a summation where I will put the value of k, and I will try to find the value of each instances. I will try to find the value of each instances of k shots, and then we did some derivation there. We did some derivation uh, from which we try to extract, we able to finally able to extract NP, and whatever the remaining equation is there, we try to convert that is equal to 1. Whatever the remaining equation that I am having, I'm trying to convert that to a 1 value, such that I will get a NP as a value. And finally, while solving by using some substitution data, uh, using some substitution that we get, we are able to solve, we are able to find that the expected value of a binomial distribution will be n into p. Okay, so this is the summary of like that. If you're not, if you are still not able to follow, don't need to worry. I will share this thing. One thing what we can do, what you have to do is, whilst you do when you started doing solving one by one, this derivation step by step, you may get much more idea like that. Okay, so I have some question here. Let's that. Okay, I can understand that some of you are not able to follow this derivation because it's something you need to do hands-on. It's something you can't do just by listening. You have to do certain some substitution. You have to extract certain terms outside to get the required terminologies that you have. So I will share this whole thing with you. You follow these things, so that we can do that. Okay, sigma summation main formula equation for probability. Can you be, oh, you're asking that what is the mean value of that? Are you asking in that way? Can you be more specific, Aditya? Okay, the sigma, okay, so if I am assuming that you want to know the sigma value of finding a probability situation here, this will accounts for, this is usually how you can represent, okay, just let me write it this again somewhere else. Usually for binomial, it depends on the situation also. So for example, right now what I'm assuming is for different case value scenarios and for binomial distributions, we have to provide k value, that is the random variable instances where it can happen, just like how we did for earlier questions, right, where we are defining x equal to 0, x equal to 1, x equal to 2. Those k values have to be there. And for the binomial distribution settings, we have to give the equation of binomial distribution of probability, that is here sigma will be remain as it is in this case. For the remaining other cases, let me, for this blue highlighted box, here the value, here the equation will change based on the distribution that you are having. So for normal distribution or Poisson distribution, it's altogether different game. So, but again, to get to that stage also, you have to do lot of, if you are put some different equation here also, you have to do lot of derivation to reach to a specific value that you usually use in your probability thing. So for that, we can do some other derivation as well if you want. Otherwise, if it is going bouncer for most of derivation, we can stop that there and we can mostly focus on solving the problems. Okay, and I will share the link of session. For that, I have to upload this thing, so which has not been uploaded. So once I will do that, I will stop the recording now. I can share the YouTube channel where I'm going to use that. Otherwise, NPTEL will share that with you. Let me